Session now, since there are 3 talks in this session. First talk is by Dieter Brechner.
I can manipulate him on you.
That you're setting up the
The rap is so beautiful song.
that should be.
Dieter is not blood.
Start with Marie then? What? Shall we start with Marie? She's here. Will you be ready? Should you be ready?
Lock the clock.
Okay, I think. Oh, but yes, send it up. Everything was locked. Let's see. Okay. Let's begin the third session today. This is going to be given by Dieter Brechner, and he's going to talk about large small-scale structure of the interstellar medium. What can we learn from HT and MHT simulation? I hope he'll tell us about, can we believe these numerical simulations?
Amongst others, yes, thank you very much. It's always good to keep an audience in suspense. People are paying attention. Much of the things that I'm going to talk have been said by Miguel or in the discussion we had this morning. So I'm just trying to give you a picture of what we think now according to our new simulations the ISM should or could be. Of course, there's much more work to be done, and I will be the last one or two to really admit that. But I think we have made considerable progress, also thanks to the computing power that we have now. And I think it's now definitely worth taking also numerical simulation seriously. Right, so I give you a brief introduction of the ISM, and I'll come straight to the high-resolution simulations, both hydrodynamical and MHD. I'll talk a little bit about the large-scale structure, which is the fountain flow. Small-scale structure, which, as you will see, on all scales you will find structure. So you need actually resolution, as Miguel has emphasized this morning already. And then, as some of the results, I will focus on the volume filling factors, on the question if the magnetic field follows the so-called Chandrasekhar Fermi law, and a little bit about the stability of gas phases. Alright, so let's start with, when God created the interstellar medium, he placed McKee and Ostriker as his popes to create a model that is now with us for a long time, and it's still more or less a standard model to compare anything to. So I'll just remind you of a few basic things about this model, which was undoubtedly very successful, but one should not overinterpret models, and therefore I think we have gone already for some time into the phase where this model has been really far overstretched. The basic idea of McKee's cycle was that you have an overall pervasive hot intercloud medium that was regulated by supernovae. And at that time that was really en vogue because it was just about that the hot phase had been discovered by Copernicus by the ubiquitous oxygen 6 line. And of course, to make a point, they stressed that the volume filling factor of this hot Chinese plasma could be as large as 50 to 70%. In this hot intercloud medium, we have interspheres, clouds, which look not very realistic, but never mind. They have a cool core that is shielded through from radiation from outside, which they attribute to the cold neutral medium. Then surrounded by that is gas in these clouds that can be penetrated by the soft X-ray background radiation, also something that had actually been discovered not so long ago at that time. And at the top of the onion here is the warm ionized medium that is actually then ionized by the UV background. Now, these three phases, well, it was called three-phase model, although you could say what is that for? There's actually a molecular phase as well that is not really taken into account here. Anyway, these phases are in rough pressure equilibrium. That was the idea. And then, as time went by, people found out that something was not all right. And one of the things that occurred was that the volume filling factor appeared to be far too high. If we look to external galaxies, for example, if we look at these H1 holes based on galaxy, as people observed later on, they found if you argue that what are holes in H1 must be hot gas, basically you come up with volume filling factors of the order of 20% or even less. Another problem was that the diffuse ionized gas was not predicted. Now we know that the ionized medium exists in the so-called Reynolds layer with a scale height of about 1 kiloparsec. So it's not just an envelope around cloudlets. And also the cold neutral medium is more filamentary than an onion shell in a cloud. And more recently, and this is what I will discuss a little bit here, is that 50% of the warm neutral medium is now found to be unstable, which is of course also not within this model. And cosmic rays and magnetic fields are left out, but that's not so much a problem for most people, although I think it is. Now, after that, there had to be some new model, and some new kind of popes arose, as always, and that was Colin Norman. And he suggested, together with Satoru Kikuchi, something that was already in the air at the time, that superbubbles, or that the supernova remnants didn't occur all randomly in the disk as was in the McGeoch striker model, but they could be clustered in space and time. And that would lead, of course, to so-called superbubbles, in which you can dump a lot of energy, as Ernst has just shown in his talk, and they would be able to break out of the disk. Thereby you really release some of the pressure, and you set up a kind of fountain flow, as it is schematically shown here. So the gas goes up, it cools down, it condensates, and then it rains down on the disk. This was actually already by Shapiro and Field, more than 10 years earlier, suggested. And Norman and Iguchi fitted this all in a picture, and of course one consequence of this kind of model is that you lower the volume filling factor of gas. Right. What are the problems here? Well, all these models are actually analytical models, and it is sure a good job that people have done looking at such a complex system like the ISM in an analytical way, but at that time computing power was still limited. And of course you get some insight into processes, but as I will argue, things get really very non-linear, and then analytic models are bound to fail sooner or later. In these superbubble expansion models in the 80s, it was always assumed that you have constant ambient density, and then you have some explosions, and then you let the whole thing expand. At that time, I remember well that we had lots of discussions about breakout, does it occur or not? The basic idea was that you had usually 2D simulations, that was the state of the art, and in 2D a magnetic field that is parallel to the galactic plane will always inhibit any outflow. So you really work against magnetic tension forces, and that can be severe. And so that's why people thought outflow doesn't really occur because you will always have a magnetic field of the order of 5 microgauss, which most of the bubbles would actually stall before they reach considerable heights. As we will see in 3D simulations, this is not the case, because one dimension makes a lot of difference. If you just think about it, yeah? You all know these problems. If you had a 2D world, how life would be with respect to a 3D world, and it would be very different. And it's the same in the ISM, because then you can actually push aside field lines and can create holes through which you can release pressure. So outflow, I don't think, is a problem even with magnetic fields, as you will see. So to summarize, analytical calculations can show us some features of the ISM, and I didn't mention the simplest hydrostatic equilibrium model that, for example, Polaris and Cox or other people favored for a long time. In the case of Polaris and Cox, they were thinking how to reduce the volume filling factor, and if you have a strong magnetic field, of course, they thought you could confine the superbubbles very efficiently, but as we all know from terrestrial plasmas, confinement is not an easy job, and it would be hard to see why it's in the ISM. So I don't think you can really confine bubbles very easily, but that's what they thought anyway. Unless the star formation rate would be very low, but certainly not in the galaxy. The ISM is disrupted by supernovae. And most importantly, something which has not been stressed here, but which I think makes a huge difference, is that the ISM becomes very inhomogeneous. Now, I couldn't resist to put this on, and without further comments, I just go on. The only reason I put this on is just to suggest that there are, of course, interactions between all the various components. And it makes it a multi-component system, and it makes it a complex nonlinear problem. And sometimes I like to compare it to the weather, to meteorology, where you also have a very complex nonlinear system, and you see that things become really very difficult, even if you have numerical power. But I think we can get some more insight now with numerical simulations, and that's what Miguel already showed this morning. And I'll try to put it a little bit in a more coherent picture. Right, so high-resolution simulations, we solve the full-blown hydrodynamic or MHD equations. You need a large grid. That's important because if you want to evolve it for a long time scale, which you have to do, then you don't want to be really limited by artificial boundary conditions, which you have to impose anyway. So in our case, the grid is 1 kiloparsec times 1 kiloparsec in the plane, and plus minus 10 kiloparsec perpendicular to the plane. And the resolution, the highest resolution we have now in HD simulation is 0.625 parsec. Now I won't go into the detail of the model because that's what Miguel covered already. We have these supernova explosions, random and clustered, with background heating by diffuse UV flux. Star formation rate is proportional to local density, and we form OB associations. Now important is the computational time scale, because as I will show, we will set up a fountain flow that takes of the order of 100 to 200 mega years to set up the cycle. So anything below that would probably miss important features. And of course also we don't want to be, or we don't want to have memory effects of the initial conditions. That's actually quite important too. Because you set up the initial system artificially. There is no way you can get around it. You have to start somewhere. And then we do it in 3D with AMR. Okay, the equations have been shown so many times, I won't go through that. So that's mass conservation, momentum conservation, all the source terms. F is the gravitational force. You also have, of course, energy input by supernova remnants. Then we use ideal MHD. And that's it, where if b equals 0 is an initial condition with appropriate momentum flux tensor, energy density, etc. And we start with boundary conditions where we inject mass and momentum and energy from supernova remnants. And the background heating, as Miguel said, is done according to this small fireball model. Okay, let's come to something that is more illustrative. This is the initial setup. So what we see here is the density. Blue means high density, that's the disk obviously, and that's the halo here. And red means very low density. And what happens now if we have supernova explosions here in the disk? Type 2 supernova, but also type 1 supernovae. as you will see, you will disrupt the disk very quickly due to explosions going on. And then it looks like the whole system is breathing according to the underlying source injection that you have. And you see lots of filaments. Here, this is really this cold gas, which some of them might come down as intermediate velocity clouds. Not the very high velocity clouds, because they have velocities that are far beyond what we can get here. Now this is the cut in the disk, and that's a 0.625 parsec resolution, and that's already evolved for 138 mega years. And so we start from there, and you already see here, this is cold gas again, this is hot gas. You see, as the bubbles become larger, they inevitably get very asymmetric. So the medium is very inhomogeneous. And this must have also consequences for the propagation of the shock. Too much? Okay. So let's see how that just goes on, yeah? You see here always explosions occurring, and what is important to realize is that if you explode a supernova in an already hot medium, the shock is initially very weak because it propagates into a medium with a very high sound speed. But then as it catches up on the wall, it becomes very strong. And so once you create these, or once you run into density gradients as you see here, then you really make things very asymmetric. So, I don't know.
Ruhezustand.
This is really stupid. I'm sorry. This is, I don't see that on video. This is Microsoft. Yeah. You can't even press an escape sequence. Okay. It wants to go to sleep now. It doesn't actually recognize the presentation as work, so it was thinking that all the time I was doing nothing here. And so it wants to go to sleep. Okay, I'm sorry.
Well, you are on camera.
Huh?
You are on camera.
I am camera.
The record.
Be careful.
I must be the main reason for it.
Okay.
Which makes it a position. Present of function. Skeptical at first, but at least interesting and is
I think so, yeah.
something is
Oh, yeah, you have to put it on. Okay. This I've never seen before. Okay. So it was going on batteries. Okay. Right. Okay. I just want to get back into the full screen mode. Okay.
Jetzt steht und da aber ich hatte.
What does it do now?
Empowering people.
That's a joke, yes. Okay. Right, so let's go back. Here are some cuts through the data cube. This is the density, so this is the galactic plane here, this is P over K, so the pressure, and this is the temperature. Here we have different supernova rates. This is the galactic supernova rates, this is a factor of 4 higher. So what you see, of course, lots of structure on small scales, on large scales, that I already said, but also the pressure is not really uniform. I mean, remember that the McKee-Ostrander predicts that everything is in pressure equilibrium, more or less at the same pressure. And in most of these models, the pressure is fairly high, because the hot intercloud medium has a large volume filling factor, and therefore the average pressure is of the order of 10,000, which here, as you can see on this color code in green, is about 3,000. But you have fluctuations. Obviously, where you have supernova explosions, something is going on. That's no surprise. But also, further away from explosions, you have structure. And if you go into higher star formation rates or supernova rates, sure, the thing becomes hotter on average, but it's still uniform. So you don't really, fill up a disk up with hot gas.
Before you move on, for the background heating, so you assume this is the UV and photoelectric effect.
Yes.
But the parameter there is the interstellar radiation field.
Mm-hmm.
So how do you calculate this locally? How do you know this locally from your supernova distribution? How do you get locally the value of the interstellar field?
It's not calculated from the supernova distribution. It's really put in by hand, ad hoc. It's not self-consistent in the sense that I calculate the radiation from the stars and produce a diffuse radiation field from that. It's a radiation field that is put in as a boundary condition or initial condition. Constant, yes. With some Z structure. Yeah, that's the Wolfire et al.
Would it be difficult to do the right thing?
In principle, no. I mean, there are other things that we have not included, which we also should include, which is not too difficult, and we will do it. Is the stellar wind phase, of course. But the argument now is, of course, stellar winds are only important for O stars, for very massive stars, and most of the power comes from supernova on average, if you look just look at the global power. But that's another thing. And in that sense, you could also put in the radiation from the stars and calculate H2 regions and so forth. Radiation transport would be much more difficult to do.
But that's done already in the cosmological context. Abel and the Canadian have developed methods that work then, so they could be used here.
In principle, yes. Yeah. But as I say, we have a long list of things to do, and
wish list.
I show you the list later on, and this is more on the back of the list. The volume filling factors, since I had argued that the volume filling factors of McKee-Ostrander are far too high, and this was the reason that normally Kiyuchi proposed the chimney model. Here, what you see is the volume filling factors of different kinds of gas ranges. I'm not saying phases here, but temperature ranges. For example, the black line is gas below 1000 K, the blue line is between 1000 and 10,000, and the green is between 10,000 and 300,000 K, and the red one is the hot stuff. So if you look at the red one, you can see that after a very short initial time, it sort of settles down at around 18%. 18% for the galactic supernova rate. Whereas, for example, the green stuff, which is in a region that is thermally unstable, settles down at around 20%. So that's certainly not something to expect from conventional ISM models. I'll come to that later again. As you see, for the other phases, it takes a little bit longer. So again, I would say 100 mega years is something that you should at least evolve your models if you want to trust them. Here, for those who are interested in higher star formation rates, and this would already be the kind of starburst, you can see how you get rid of the cold gas. As you increase the supernova rate, of course you increase the hot gas, but even in the case of 16 times the galactic supernova rate, we don't actually get more than 44% in the volume filling factor. And the reason is the fountain flow.
there is no cold gas. How stuff unless where you then explode the supernova, there is no cold gas.
I mean, eventually you set off star formation, that's right. If you really get rid of all the cold stuff. But remember, we don't have the molecular gas in here. That's also a deficiency of the model, if you want. But that would include self-gravity, which is on the list.
What if you listed mass fractions instead?
What if I would or if I could?
No, what if you did?
Yes.
They would vary much less. No?
Well, most of the mass is in the molecular phase. Then comes the cool gas, and of course what we have here in the hot gas is negligible.
In the case of a much higher supernova rate, compressions are stronger. So the cold phase has a smaller volume filling factor, it's denser. And therefore the density would vary, or the mass filling factor would vary less than the volume filling factor.
I'm not quite sure about that. I mean, if you have a high supernova rate, you create a lot of hot gas. I mean, also this is a lot. Half of the disk is filled with hot gas.
But it's also hotter, so it's thinner.
Yeah, but compression becomes lower. If the upstream medium has a higher temperature, shocks get weaker. So I mean, we could do that and see how it actually is by mass. But since the volume filling factor is usually, given in times of...
This is because they can be observed.
Well, that's not a thing which is really unreasonable. Sometimes you should also calculate observables in your model.
But not always.
The
good thing about models is that they give you access to things you can't observe.
Yes, and you can make predictions of things that nobody will ever observe. Right.
You need to calibrate them. But then you need to use them also to find new things.
I'm fully with you. I mean, I'm a theoretician, so you don't have to convince me of these things. Right. So, as I already said, the volume filling factor is low because we actually have possibilities to get the gas into the halo. That acts like a pressure release valve. Now, somebody asked me, can we believe numerical simulations? Thank you for the question. He did. Since I was working a long time analytically on these things, and I basically didn't get anywhere, so I was naturally very critical with numerical simulations, because I thought, if I don't make progress, why should they do? And you had lots of reasons in the past, I mean, you still have lots of reasons now, but even also in the past to be very critical. And one thing I think is crucial that people don't really address as much as they should, I think, is that the results you produce should at least be resolution independent. That's, I think, necessary. It's not sufficient, but at least that's something I would really require. I mean, normally people, you laugh, but normally people say, well, I'm going to the limits of my resolution, and I put in as many processes as I can, as long as I have computing power and resolution. But of course, what do you learn? You increase the resolution, and the picture looks different. And that, I would say, in that case, I wouldn't believe it. So, what you see here is, for example, the smallest scales that matter in our simulations, which have not so many physical processes as these of other people. So here's the maximum density or the minimum temperature, for example, and here you can see it better. And the various line color coding is that the black is the highest resolution, 0.625 parsec, red is 1.25 parsec, and green is 2.5 parsec. And you see a convergence. I mean, the green line is still way up here, but if you go down to 1.25 parsec and then to 0.625 parsec, then things look more or less the same.
But it's a pretty stiff scale.
Well, there are fluctuations, of course. I mean, but still,
even the systematic difference is almost a factor of 2.
Yeah, well, that's nothing. Look at the green curve.
Yes, you need that one. That's the one you need.
Well, now you're getting really, I would say, ungrateful.
Yes.
Because I already consider this as an achievement, because as I say,
I'm joking.
Many people don't care, I know. Okay, so, as I say, a necessary condition, not sufficient. Right. So far, the magnetic field was not in the calculations, and the usual question is, how do your solutions stand when you put in magnetic field? So, here is one answer. What you see is again the Z direction here. This is the color coding is like red is high magnetic field strength, blue is low magnetic field strength. We evolved from a state already 300 mega years, and what Miguel also showed this morning, and you can see it here, you have this loop structure here in the B field. So apparently, and that's what I said yesterday in the discussion, what happens is that the supernova explosions or the superbubbles that break out of the disk, they drag the field along. And I think, if I look at these movies at least, they are probably more efficient than the Parker instability in the beginning, at least. At larger heights, I would agree. At some stage, when the gas comes down again, the cosmic rays probably can help in dragging them out further. But if you really have lots of power in the disk, then probably supernova remnants or superbubbles alone would do the job. This is the density here. Color coding: blue is high density, red is low density. And you see also lots of structure, even in the MHD case, and breakout, as you inevitably can see, is not prevented with magnetic field simulations. And finally here, this is a cut through the disk, just a very small time sequence because I'm running out of disk space with this old laptop here. But what you can see is here are high field line regions. Where you have superbubbles, of course, you really move out the field lines to the walls. So you form compressed layers that also have high magnetic field.
How strange, there are structures that don't move at all.
Yeah, that's true, because this is gas that is very, very dense. It has a very high inertia. Yeah. Here to see without moving. So what we see is, the important point at least I think, is that you cannot prevent the outflow, because as in 3D you can actually push field lines aside. You may even be able to create quasi-open field lines, and if you have magnetic reconnection, which has to work, although I'm always cautious with the time scale on which it works. And if you think it works on a time scale given by length over the alpha speed, then you are being very optimistic. Nevertheless, it should work. And these holes, they act as pressure release valves again, and for that reason, the volume filling factor with magnetic field is not so much different than for the pure hydro case, which is a little bit surprising, but it tells you that once you create holes, you can actually get rid of the stuff there. And you generate loop structures as well. The density shows you actually some sort of clumpiness. You don't have smooth flows really. That will also be interesting for shock waves propagating out into the halo, because they would really shock these clumps. Okay. So, which ISM component controls the dynamics actually? That was already raised this morning, this question. Is it the thermal pressure, is it the magnetic pressure, or the ramp pressure? Now you can calculate the average pressure, and this was the picture Miguel showed this morning, and I just repeat here, for a large temperature range, for these average pressures, the ramp pressure is actually dominating, and that really must tell us something, that the supernova-driven ISM dynamics is very important. So it's not an ISM as in the old picture where you have just three phases coexisting very peacefully, but it's a very messy situation. Do I get some money?
Yeah, and you think
Sir, this implies that the turbulence is very strongly supersonic, right?
Yes.
What numbers are those three?
This is true, yes, and as I will show you, turbulence is actually fairly high, and it can even be super-Alfvénic. Right, so, as I say, the cold gas, which is the red line, the magnetic pressure, which is the red line, is dominating up to temperatures of 100 K. And this what you saw in the movie, these things that didn't actually move were high field strength cold gas. But as you go to higher temperatures, then you go to the ramp pressure dominated region, and then at around 10 to the 6, then you are actually in the hot intercloud region, and then the thermal pressure dominates.
That really must be wrong at the low temperature. It must be due to bad resolution at low temperature, because we know diagnostically that the ram pressure is dominating magnetic pressure at the low temperature as well.
From which observations?
About 5 or 6 different ones, where we do synthetic model observations, everything from extinction to temperature, velocity correlations, everything. Nothing works if you have dominating magnetic pressure at low temperature.
Why is the magnetic field frozen in at low temperatures? No ionization speed.
Why is it frozen in?
Yeah.
Because this is ideal MHD here.
I know, but that's an unrealistic picture, surely.
Okay, I agree. Of course, you would have diffusion effects eventually, yes.
Well,
But-
certainly that's
yes. Okay, no, that's certainly true, but this is not in the model, so I cannot say how big the effect really is. Okay, as you see here, I mean, the domination is not like by many orders of magnitude, like between here or here, but I would think that if you have cold gas and you compress it and the fields are frozen in, if this approximation is valid, of course, there are things like ambipolar diffusion or so that give you some field diffusion, then you should also have a higher field strength where you have a higher gas density. And that would increase the magnetic pressure. Well, right. So you would certainly agree that ram pressure dominates lots of the ISM dynamics.
Oh, yeah.
Okay. How is actually the magnetic field connected to the density? And there's the original idea that is still used very often because it's quite convenient, brought up by Chandra, Sekhar and Fermi in a classical paper, where they actually looked at the deviation of the planar polarization of starlight in the spiral arm and the deviation from the direction of the spiral arm, so to say, due to random motions of the B field. And these random motions are induced by gas turbulence. And it's a very easy calculation, so I just show it. What you look at, the transverse oscillation of the field line. That's just a cosine wave, where v is the alpha velocity. You take spatial and temporal derivatives, and then you find out that the mean squared derivative, spatial and temporal, are connected in this way, with, as I say, v the alpha speed. If the RMS velocity is due to the turbulence, which they thought were just clouds that were moving around randomly, then if you would think that this mean deviation, which at that time was measured to be 0.2 radians or something, is connected to the spatial mean square, y prime squared, average is a squared, then you can just plug in these things and you find that the B field must follow this relation. So B proportional to rho to the 1/2 and V turbulent and A were actually given by observations. Or in other words, the turbulent velocity is actually linked directly to the alpha velocity. So if this is true, then you would expect a straight line, like V proportional to rho to the 1/2. What the simulations show here, that this is actually, even for an astronomer, I would say a poor correlation, that you have big regions. Now we plotted it here for different gas temperatures. Here's, for example, the hot gas. It spreads over, I mean, they all somehow overlap with this line, but you have lots of data points here that are outside this line. Here's the green stuff again, which is the unstable gas. Blue, as we know, is between 10 to the 3.9, 10 to the 4.2, and etc. And black is the cold gas, the same color coding as before. So, what can be the reason that this correlation is really so poor? Well, one reason is, of course, that the flow is ram pressure dominated, and the turbulence that you create is very strong turbulence, as was already said, and it can be supersonic and superalphanic. And so, in this case, there need not be such a correlation like we have here. As Miguel mentioned this morning, other people have investigated this as well, and they come actually to similar conclusions. But here we see it for a large-scale simulation. That's probably the new thing we have done here. Right, and coming slowly to the end. Just briefly, the PDFs, the probability density functions that you can create out of these simulations. And I just want to show you that this is the MHD simulations where this is here is density, here is this the n by the n, the integral gives 1. So this is the total of all various components, and it's just broader for the HD than it is for the MHD, simply because you have, of course, magnetic field that also goes into the compression in shock waves. The stability of gas phases is something which I think is fairly new, but is now reported by a number of people. And this is something which is actually observationally found as well. Karl Heinlein has done H1 observations and the warm neutral medium, and he finds that almost 50% is in a classically unstable phase between 500 and 5000 K. And that's, I think, a very important observation, because that tells you something that with this normal ISM models must be wrong, because no classical ISM model that assumes that everything settles down to stable phases can produce this. And we find that, for example, in a regime between 10 and 8000 K, about 80% of the gas is unstable. In this temperature range here, we find 55%, so we are fairly close already. Maybe too close, but we will see as we put in other processes. Okay, does this contradict the classical stability theory? Not necessarily, because stability of phases, if you remember, was derived in a time asymptotic limit. You assume that instability means that the cooling time is less than a dynamical time scale. And the stable points of your plasma are determined by the properties of the interstellar cooling function, because just the cooling function has this funny shape. This allows you to have stable points. Now here, we have time-dependent and dynamical pictures, and this, as I said already, can be different because we have strong shock waves that can heat up gas that is cooling down. We have turbulence, and my personal opinion is that if the eddy crossing time, for example, is smaller than the cooling time, then you can actually prevent condensation, which you normally, in the classical stability analysis, would not do. And that could be one reason that we have so much gas in the unstable phase. So coming to the end, the global picture I would draw from the ISM until now is, depending on the star formation rate, large bubbles break out of the disk, and especially for the Milky Way star formation rate, it cannot be prevented even by a magnetic field. You create loop structure that are driven by outflows, and these outflows act as pressure release valves, and that reduces the volume filling factor. The supernova remnants and superbubbles in the disk are responsible for the generation of supersonic, sub- and supraultrasonic turbulence, and the flows are largely then pressure dominated. The clouds, I didn't say this, but you have seen it in the simulations, are really filamentary in structure. These are these blue worms that are shock compressed layers. So, to summarize, numerical ISM studies can reveal many new features as compared to analytical studies, and they are meaningful if I think you choose a computational box and evolution times that are big enough so that you get rid of memory effects of initial conditions. If your simulations are not resolution dependent, of which, or most of which are actually, and if you include the most important physical processes, and here we definitely have to do more work. We haven't put in self-gravity, so the star formation rate as we prescribe it is ad hoc, although consistent with observations. We haven't put in cosmic rays. We haven't put in, you tell me, for example, non-equilibrium ionization, which is something I think can also play a role. So the supernova-driven ISM contains structure on all scales and is inhomogeneous. So any estimates that are based on, suppose that the ambient density is constant and blah blah blah, are to be taken with care. Okay, I said that we have high level of turbulence. I said that the B field doesn't follow the Chandrasekhar Fermi law. And just as an outlook, I would say that we could even probably produce a magnetic dynamo, and here I'm referring to Axel's work more than 10 years ago, where he showed that in a galactic wind you can actually have a dynamo. I think in a turbulent fountain wind flow this should be possible. I also think that you could have re-acceleration of cosmic rays due to random motion of waves in the disk, and also as the work that Ernst and I am doing, you can also have re-acceleration of the cosmic rays in shocks that are propagating through galactic halo. So there's a lot to do, but I think you shouldn't give up, not at this stage at least. We are having already had enough discussion. Can we just take one or two questions, please? I think that the general discussion will be important.
This thing about self-gravity, how do you propose to do it? You can't just include it, because if you do, things are going to collapse and time is just going to freeze.
Well, there are. Okay, I'm not the expert on it, but I do remember that there are models that where people take it into account, namely people who do star formation calculations. They calculate much smaller boxes. Yeah, they want to produce a cluster and they want to produce the initial mass function, etc. So they must have some clever Poisson solver, which I'm still not sure which one we should take. But of course,
but that's not the problem.
It should be possible in principle.
Computing the gravity is not a big deal. It's not going to take much time. The problem is that when things collapse, the time scale becomes terribly short, and you have to follow it, and therefore you can't get any time
The real scales will get more good immediately, right?
But of course, you would have to cut it off at some stage, that's clear. Where it becomes unrealistic again, but...
Then you have to make a sync particle and forget about that particular thing. But even that, if you want to really cover star formation, the scale is going to be very small.
Well, I'm actually not so much interested in the star formation as it may sound. I'm more interested in the formation of molecular clouds. And that we cannot produce now, because first of all, we don't have a cooling function that has enough molecular lines, and second, we cannot resolve the scales we actually need for molecular formation. And what happens then after molecular clouds, i.e. the stars, that's a different matter. This ambition I don't have.
Is it possible to derive power spectra? Main question, is it...
For the turbulence.
Is the interstellar medium or turbulence Kolmogorov or non-Kolmogorov?
That's actually... That's something we just want to do. But I can't tell you what it is now, but that's something that is also easy to do.
You might have some idea about which resolution you need just on analytical grounds. I mean, given some group coefficient or whatever, is the scale where it starts converges at consistent with that, or are these completely...
Oh yeah, that was this curve Miguel showed this morning.
Yeah, I think there was some.
And you've seen there was an exponential term, and at the denominator there was the length scale over which this really would converge, and this was 1.1 parsec or so. And this actually coincides very nicely with what we find from the simulations. But I don't want to overstretch this, because, as I say, it's a sufficient condition, and if you put in other processes, I think that's the major point here, then you might need much higher resolution. I mean, if things operate on small scales,
Last question.
You cannot claim.
Can you say something about the observational confirmation of the Chandra sequence? Is there any text? It seems to me that I've seen a picture, maybe this is in the article by Valet about the review paper about the magnetic fields in the universe. Then there is something like a very good correlation. I don't remember what is the power index, but it seems to me that the correlation is quite good.
It's an upper envelope.
Pardon?
It's an upper envelope. The maximum field you can have at a certain density correlates very well, but you can have many different fields.
Well, plus there is basically no dependence on the field of density for densities up to about 10 particles per cubic centimeter. And only at larger densities, this upper envelope develops with root of n at larger densities.
In this context, can we compare this kind of envelope to the simulations? I mean, in the picture you have shown that the points are spread very much, but even if there is an envelope, it would not fit very much to the simulation.
But the range above 10 or 200 was just the right corner cube diagram, which of course that didn't dominate. But I think that, like that was there in the diagram.
That is it was fitting better for the higher densities, but we cut it at
300 or so particles per cc. I remember there was a paper by Joe Silk and somebody else who investigated this, and they put in lots of other processes that would actually change the spectral index of this law, and they were arguing that this was driven by observations. There were observations that show that it's not 0.5, but it's something else. But I don't recall.
It's not far from 0.5.
I think further discussions we can have it in the general discussion case before it's anyway. My copy. The role of the magnetic rotation instability in galactic distance.
On your T-shirt.
Yeah, there is actually the case.
Das ist eigentlich nur.
I can continue actually.
I can continue.
You can continue.
That's really good, huh?
Sometimes the other part of the school cannot.
Okay, so today we have heard a lot about supernova regulated flows, a lot of interesting things. We have also heard that the supernova explosions overwhelm all kinds of other sources of turbulence in the ISM, and now I'm bringing up this MRI instability. So what can be the role of the MRI in galactic disks? Do they have a role or not? So what I'm going to talk about today is kind of moving a little bit away from the self-consistent, or a model what you can call a self-consistent model. Because what I'm going to do is, or present, is like a parameter study, rather than trying to fix everything, fine-tune everything, and let it go and look where it develops. We have rather vary some parameters like rho, T, supernova frequency, cooling, lambda, and so on. And by doing all this, we kind of fix the initial condition to describe different kind of phases of the ISM, from the cold to the warm, and then to the region dominated by supernova explosions. And then we investigate whether the MRI really has a role in there or not. Since I'm the first speaker to talk about the MRI, I just thought I would remind everybody here what this magneto-rotational instability is. What we need to ignite is rotation and shear such that the angular velocity is decreasing outwards, plus a weak magnetic field such that the ratio of the thermal to magnetic pressure is large. But you can formulate it, I will show it later. For the vertical modes, you can say if beta is larger than 1, then you can expect the MRI to work. Here is just a simple sketch to show how the instability is ignited. So here are just two mass elements. This is a vertical magnetic field line. It's not. This magnetic field is now weak. It's, let's say, fulfilling this criterion. And the shear is trying to, these mass elements are displaced just a small amount in radius. So the shear is trying to pull them apart because they have a different rotational velocity. But since there is a magnetic field, it has a force. It will try to pull these things back towards each other. And the effect of these mutual forces is to remove some angular momentum from the one that has less and donate it to the one that has more, and this process increases the angular separation of the mass elements, and this process kind of runs off. And this only happens if there is a magnetic field. The magnetic field must be there, but it can't be too strong. Otherwise it resists too much, and these mass elements will not be displaced. And when this MRI is ignited, then it leads to angular momentum transport outwards and acquisition of matter inwards. And then energy is tapped from the shear flow effectively both to the kinetic and magnetic reservoirs. And in the nonlinear regime, then you end up, in 3 dimensions, you end up with fully developed MHD turbulence. And one special property of this MRI flow is that the magnetic field energy is usually larger than the kinetic energy of turbulence. And this instability has been very extensively studied in the case of Keplerian nitrogen disks. Here is just one example of a close paper, 1995. Magnetic energy versus time, and kinetic energy of turbulence versus time. And here the magnetic energy is dominating over the kinetic by a factor of 3 or something like this in the end of the simulation. So, the galactic disks then, can they be subject to this instability? So it's well established that galaxies rotate differentially, and the angular velocity is really decreasing outwards. For example, for the Milky Way, we have a flat rotation curve. And it's quite easy to think that at some point of the galactic evolution, when the galaxies were young, there was a weak magnetic field, so that this large plasma beta condition would be fulfilled. But when you contrast that to the present-day galaxies, where we can say that there is rough equipartition once more, with a turbulent kinetic energy, trace one could add there. The galaxies are actually, at the present day, they are low plasma beta environments, where these betas are roughly in the order of 0.1 to 1. So they are just in the limit that the MRI could work. And then we also have this other puzzling factor that we already know, that the supernova energy input is so powerful that at least in the star-forming regions it's overwhelming everything else. So these 2 reasons probably have stopped people to look at MRI for galaxies. Now certainly that is going to change. So why do we then have to bother about the MRI at all? So first of all, let's look at the plasma beta. Is the plasma beta really in the regime that the MRI cannot be ignited in any circumstances? So if we take the linear theory of Garbus and Pauli, 1991, 92, and so on, it's an extensive set of papers, you can write the stability criterion either for the wavelength, which I have marked here with a lambda critical set, just indicating that this is the vertical mode, or in terms of the plasma beta in the vertical direction now, by requiring this critical wave number, this is the smallest resolved wave number, fits to the disk which has now a scale height of 8. This condition, this wave number will fit your disk if and only if this plasma beta in the vertical direction is larger or equal to 1. And here, rho, this is the sound speed, this is the vertical magnetic field. If you plug in the galactic parameters and compare this to the total plasma beta wave, which you obtain by replacing V naught set here by the P total magnetic field strength. So the total field could be 7 microgauss at the solar cycle. The vertical field is much weaker, so it could be 0.4 microgauss. So what you obtain for the total plasma beta, okay, it's really small, 0.5, but this vertical plasma beta is of the order of 150. So things are okay, at least for the vertical MR modes. And then, do we really need this? The plasma beta may be okay, but do we really need this? And there comes, some observations come into the picture to tell you that maybe you really need this. And already Sami was this morning talking about these observations. For example, in the outer regions of some galaxies, you still observe significant velocity dispersions outside the optical edges where the supernova frequency is really low. And these turbulent velocities, they are tending to a constant. This is the graph Sami already showed in from BK4 1990. So you approach something like 6 kilometers per second at the radius of 10 kilopascals. On the other hand, we know, as Sami told us, that even galaxies with low star formation rates exhibit significant velocity dispersions. He was already explained. Nevertheless, even though 100 times smaller supernova rate or star formation rate will result in significant velocity dispersions. So what happens in these galaxies? You meet another source and the supernova explosions. Another puzzling observation is that the scale length in some galaxies, I think now it's, the sample is very small. I only know full derivation for one galaxy, which is made by Beck. It's for MTC 6946. In this galaxy especially, the scale length of the magnetic energy density is much larger than that of the supernova distribution, which is 2 kilopascals, or the turbulent kinetic energy. And this is plotted in here. And so this galaxy, the plasma beta, you can estimate it. It's roughly 0.1 when you divide this by that. But what's more puzzling is the radial behavior of the magnetic field energy density, which doesn't fall off as quickly as the turbulence. And this is once more an observation which is relying on the equiposition argument between cosmic rays and the magnetic field. So are the outer parts of galaxies really magnetically dominated? Okay, so it seems that at large radii, or then in galaxies which do not form stars very frequently, the supernova scenario just won't do. So you have to have some other source of turbulence. And as we already know from accretion disks, the MRI would have some desired properties like the super equipartition magnetic field. So there seems to be also need or motivation to investigate the MRI for galaxies, and since 1999 people have realized that, and now a lot of people are working in this field in addition to us. And I think the starting point of all this was the paper by Selwood and Balbus in 1999, who involved the idea of MRI driving the turbulence in the outer region of galaxies to explain the sticky at all velocity dispersion curve which flattened in the outer part of the galaxy. Then some years went by, and now there's a Ivo Stryker and Kempek just recently published a paper where they showed a very important thing. Because in accretion disk simulations was more or less a diffuse, totally smooth distribution of gas where this MRI was working. But the ISM is not smooth. It's a multi-phase, multi-component medium with a lot of molecular clouds, filaments, whatever. It's not obvious to think that in this kind of medium the MRI would naturally work. So they showed in 2D that this MRI channel solution can appear, so which means that the MRI is ignited in a medium where there is clouds and a diffuse component. Here's just one plot from the paper where they start with some molecular clouds embedded in a diffuse medium, and after 2 rotations they get this channel solution, radial streaming pattern generated. And the clouds are reshaped by the thermal instability because this gas is in a thermally unstable region. And then the Potsdam group, Natalia and Peter will talk about this. They have been also modeling the MRI, but in a global domain. And what we have been doing is first of all, we confirmed this Piontek or Stryker result in 2D and extended it to 3D. And now we have included stratification and then dropped this idea of imposed magnetic fields first. We just use the initial condition for the magnetic field. And could have added this as well there. We just impose some initial conditions to the magnetic field, after which it's free to develop wherever it pleases. And the model is a local Schulenburg's model, which has already been presented here, so I don't have to go into details. What is special about this is mainly the rotation curve, which we adopt. It's not anymore Keplerian, but it's a flat rotation curve with a shear parameter of q equals 1. Then we fiddle around with the cooling function and UV heating. We basically take the wall-fired wall cooling curve and then fix the UV heating so that whatever initial condition in rho and T we choose, the ISM is always in hydrostatic equilibrium, so that it doesn't start either collapsing or expanding. So then we are able to investigate several kinds of parameter regimes where rho and T are changing. Then we just inject or initialize a vertical magnetic field with a plasma beta, something like 1000. Equations everybody has seen. So now I will not go into the details. What will happen in the MRI case? How does it look? Just going to now go through the parameter regimes which we have investigated and where we find the equation of the MRI instability to work. This is an example of the energetics and the plasma beta. This is kinetic energy, magnetic energy versus time. Everything is versus time. This is the plasma beta parameter as total plasma beta, and the critical wave length for the MRI. And this is just an example of one calculation with 128 cubes in 1 kilopascal box. We have made several in this temperature regime. This one is near the temperature 4 Kelvin. Here I just show what really happens in the system. So during the first couple of orbits, the thing gets unstable, which is seen as the growth of kinetic and magnetic energies. Then they grow, they oscillate a bit. The plasma beta parameter was initially 1000, so this is logarithmic scale. So it goes down as a total to a few tenths, having local minima of 0.1 to 1. Critical wave number is few hundred parsecs, which is plotted here, so it's fitting this thickness. And the magnetic field generated in this system is such that this critical lambda and the plasma beta, they are in the limit that the MRI keeps working, keeps going. And as in the case of accusing this, we get significant amount of turbulence. The URMS velocity in this calculation is 4 kilometers per second. We get a dominance of magnetic energy, so that the ratio is roughly 3, which is typical, already observed in the previous cases. And since we include the galactic shear, the whole thing is really strongly governed by the atomical magnetic field and also the atomical flow. Then if you just go from this temperature regime to the hotter end where supernova explosions become important. This is just an example of a calculation with a supernova frequency of 1/3 of the galactic rate. We have done several runs. The lowest case investigated was 1/10 of galactic frequency. But this is again quite similar behavior by varying the supernova rate. what happens is the system gets turbulent, and the turbulence is very, very strong. It's much stronger than in the MRI case. So you get URMS velocities which are higher. The magnetic field energy is also growing, but it doesn't grow to the equipartition value even. It's something like 10% of the equipartition value. Total plasma beta is, we start with 1000, and we keep it going in a very large value because supernova heating heats gas, and the magnetic field doesn't grow too much. We still have local minima of plasma beta of 1 to 10. The critical wavelength, put it in here, is the same order of magnitude than in the MRI case, but the ratio of the vertical field to the total field is very small. So the vertical field is very weak. It's only 1% of the total field. So what actually happens for your critical wave number in Z is that it gets very small. It's these two things, you can immediately scale these things. So the critical wave number, wavelength in the vertical direction is very small. It's something like half the scale or a little bit above that. Pasek, yeah. Yeah. So actually, in the supernova force flow, the MRI cannot be any more resolved because our resolution is something like, in the best case, a few parsecs. So when you let the magnetic field evolve in this supernova flow, it will evolve in such a manner that the MRI doesn't just, it can't work because not all the criteria are fulfilled. Then when you decrease your temperature below 3000, roughly 3000 Kelvin, you go to very, very thin and very, very cool disks. There, the cooling time scales become very short, and the thermal instability kind of takes over immediately. In a few tens of years, everything has become extremely turbulent due to the thermal instability. So the kinetic energy of turbulence, you get significant velocity dispersions. It's the same order of magnitude as in the case of the MRI. So a few kilometers per second. And you maintain that. What happens to the magnetic field? Well, the magnetic field doesn't like this flow. It's at least, now you have to notice that this time span of the simulation is much shorter than in the case of the MRI and even in the case of supernovae because the time scales are very, very, very short in these calculations. So it's possible that this magnetic field will eventually start growing, but at least in the supernova case and in the MRI case, in any orbit it was already exponentially growing and almost saturated. So in that sense, you might expect that there is no dynamo or any kind of amplification of that field in here. Again, you get the vertical field, what you get is very weak, and the total field is also very weak. So of course your lambda critical is now very, very small. And the vertical lambda even smaller, so you are in the sub-parsec scale. So in the thermal, in the very cool or cold disks, you end up in a situation similar to the supernova case. The lambda is too small for the MRI to operate. So all in all, we have kind of, by doing this parameter research or investigated different kind of parameter regimes, we have found a regime of 3000 Kelvin to 10,000 Kelvin where the MRI really works. If you inject too many supernovae, it stops. If your disk is too cool, it stops as well. And since this is a cosmic ray workshop, I thought I have to say something about the cosmic rays. Yeah, so first of all, I wanted to put forward this once more, this equipartition argument. I mean, the motivation for doing this research, at least for me, was partly because the observations seem to indicate that maybe the outer regions of galaxies become really magnetically dominated. But these observations are relying on the intercondition argument or assumption. So it's very essential. Well, of course, we need more systematic observations because now it's like few galaxies or only for one, but I know that there is really these curves really established or derived from the observations. But then, in addition, you need this relation between cosmic rays and magnetic fields, and we already heard yesterday that we don't actually know how this versus radius. And models like mine presented here in general, which exclude cosmic rays, they may not be directly useful to determine this important relation, but maybe they are useful in the sense that in this kind of three-dimensional data cube, we really have this correlation between the magnetic field and the density. And if you include ionization, then you know also the number of electrons and stuff like this. So maybe they prove useful just by making analysis, assuming different kind of functional relations and then comparing to observations. But of course, finally, eventually, models including cosmic rays have to be developed. And I already expect that whatever I have said today will change quite a bit if cosmic rays will be included. For example, talking about the MRI case. The MRI case, or MRI diamonds, they are very sensitive to the vertical stratification. Because there, I mean, if there is any cosmic ray gas which is contributing to the pressure, vertical pressure profile or gradient, then this disk thickness and disk properties will change, and the properties of the MRI will change. And also, at the moment we have very carefully scaled, there is no particle instability, nothing like this. We have chosen the initial conditions so that this particle instability will not interfere with us. But when you have this thermal instability going on, or supernovae going on, even if there is only a few, you may trigger it, and that will also change the dynamics. And well, I leave you with these conclusions. Thank you for your attention.
In the cold phase, what was the Mach number approximately in the case where you didn't have a dynamo? How large was the Mach number? Was it supersonic already?
Yeah. Yes.
So possibly the magnetic diffusion is very large, right? In which case maybe the resolution was not enough, or the Reynolds number not enough to get a dynamo.
Yeah, there's a lot of certainty going into this end of this. And,
is it not true that the critical wave number is a minimum wave number?
yeah.
All the longer modes are unstable.
Yeah,
and so far it's no problem if the critical wave number is very small. That means only that everything is unstable by MRI.
The longer, very reduced growth.
Yeah. They also reduce.
You should be a bit longer, then you will see the because the longer modes they will grow a bit slower.
Yeah.
So there's different ways and so on. So if you run so short simulation, you don't see it.
Well, 10 orbits is already, it's 10 orbits, it's 2.5 gigayears. Nevertheless,
Maybe I was distracted, but you wrote that you investigate also the effect of the density, right?
well, in the sense, if you go and figure, if you go and fiddle around with your heating and cooling, when you go to very strong cooling, your density range is getting, it's kind of spreading out. So in the simulation where you really go to the cold temperature end, your maximal, the cloud densities are much higher than in the case of less cooling. That's the effect of these two. But you can also start with a, varying the density as well.
Any other questions?
How would your calculation would change if you allow for partial instability evolution?
Oh, that's a good question. Yeah, that was my point. At the moment, we are really careful. We are scared about the partial instability in the sense that we don't want to have it because we wanted to isolate this MRI kind of business. If we would have a partial instability of any kind of loop,
calculation with all instabilities inside.
Yeah.
Which completes interesting check.
Yeah, but something that we haven't done for some reason. We try to isolate the MRI.
Thanks, Stephen. Last talk today is Gunther Riegler on global risk models, that's MRI and contact.
This is too dangerous. Okay, that's the last part, and I promise you it is so far more simple than the others, as it is completely linear. What is MRI? My collaborators here are Leonid Kuchetinov, Dima Shalipkov with Leonid with the MRI, and Shalipkov with the Hall effect. What is MRI? MRI is understandable very easily. That means if I have here a sphere and a differential rotation, and the differential rotation has a negative gradient outwards, decreasing outwards, then it is in hydrodynamics nothing happens. But if I add here some magnetic field, also in the same sphere, and this magnetic field is neither too large or neither too weak, then it's unstable. The differential rotation law, the rotation law here in the sun, this was the sun, this is another talk, is unstable. That's it. Nothing else. But there are two limits. A lower limit of the, this is the differential rotation, and now after a while it is light green, that means it's rigidly rotating. It is also easy to understand if we solve the equations of this momentum equation and the induction equation, and do not forget the Lorentz force, then in the local approximation one can find some dispersion relations, and the condition that there is an unstable solution is written here. That means if this is the Alfvén frequency, this is a little bit wrong here, this is omega A, is smaller, the magnetic field is weaker than some limit, and this limit is of course must be positive. That means it works only for rotation laws, decreasing outwards. We do not know any rotation law which is unstable, increasing outwards, except at the end of my talk I present one. This is with Hall effect included. That's the only one.
The case of the wave numbers of what?
The K is the wave number instead of the disturbance. The dispersion relation
of the magnetic field disturbance.
No, of the disturbance of both.
Okay.
It's a Fourier mode. Both. Okay, so we can understand it. The simplest formulation of this condition, that means the magnetic field must be small, must be weak, compared with the critical scale and the rotation is by Velikov, 59. He comes from the community of the Taylor-Koyev, magnetic Taylor-Koyev flow. This critical wavelength, if the correlate of this length here, the radius for the sun is 1 Tesla. In the evening I shall give you some stories about the old history of the in astrophysics of the magnetic rotation and stability. In astrophysics, Fricke from Göttingen was the first who found it, but then he became an observer and forgot it. Now I switch to magnetic fields in galaxies. What I see here is we have strong vertical fields of say 10 microgauss, and the symmetry seems to be the parity, the symmetry with respect to the equator seems to be quadrupolar. Another example is this. I forgot the name of this. It's the same?
4631, right?
What I see here is wonderful quadruple symmetry. So we have a quadruple. But if we have to explain quadruples with dynamo theory, with the classical dynamo theory, we have a problem. We need a seed field with the same symmetry, with the quadrupolar symmetry. That means, in the language or expressed with currents, we need a current system which is antisymmetric with respect to the equator. By means of a battery effect, that would mean that also the flows must be antisymmetric. The velocities, the motions must be antisymmetric with respect to the equator. And such flows in the collapse do not exist. This is the argument by Carlson and Beck in the paper by 98. We have, in order to explain quadrupoles by normal mean-field dynamos, we have a seed field problem. We have no quadrupole. We cannot explain with battery effects, for example, quadrupolar seed fields. We have I have only 20 minutes.
That's it.
Huh?
It's not batteries that produce a seed field, and that's it.
No.
There are many other ways to produce a seed field.
Read this paper.
All you need is a small bit of field.
Yeah, one can make a lot of remarks, but this argument is very strong. You need a quadruple, and so on and so on. Read this paper. I believe it is very good. So we have also another problem. We have the problem that in contrast to stellar magnetic fields, where we have pitch angles of say 10 to minus 3, we have here pitch angles of 1. That means the order of the toroidal field and the poloidal field is the same. This is not easy to explain. Whereas the differential rotation, of course, produces small pitch angles. There is a paper, or there are proposals to explain this effect by internal global flows, but for a simple dynamo it is very complicated to explain. Pitch angles. So, Anwar, we have a discussion time. We have a third problem, and the problem is even the youngest galaxies seem to have magnetic fields of order of microgauss. That means we also need for the dynamo a rather short growth rate, a rather big growth rate, a rather short growth time. Okay, this is the setup. This is the formulation of the problem. And now Leonid and Mazur, some PhD students of him, developed years ago some global model in order to solve the magnetohydrodynamic equations. With shear, this is the linear velocity, and here is a rigid rotation, threaded by a magnetic field, and with some boundary conditions, of course, Q to vacuum, and so on and so on. And the main point now is, what we have to take into account is that the viscosity is much larger than the magnetic diffusivity. That means we have this exceptional situation in the universe of very high magnetic quantum numbers. And what we did is to ask, is it possible to apply this mathematical model to the MRI problem in order to find the limits of the magnetic field? The lower limit for the MRI and the upper limit for the MRI. And we did it. At first I have to introduce some dimensional numbers. This is the magnetic quantum number, you will know it. This is the magnetic Reynolds number, normalized with the magnetic diffusivity. This is the Hartmann number. It's a normalization of the magnetic field. And the Lundquist number is also a magnetization of the magnetic field, but without the viscosity, with the molecular values. I mean molecular values, in order to find which is the minimum magnetic field, which is for which the MRI is working in such a global model in such a global field with the correct, or rather correct, rotation law and with very high magnetic bundle numbers. What is the limit? Is it possible that the seed field problem can be solved by MRI? So this is the result, very characteristic equations and very characteristic figures. Here we have it. Indeed, for such a magnetic Reynolds number, that means shear, 40 here for example, we find that for a bundle number of 1, this is the world of the simulations, we find a lower limit of the Hartmann numbers, that means the magnetic field, and the upper limit. Here we have stability, here we have instability. For the bundle number 10, we have practically very similar situation. But not here. Here in the minimum. This is the minimum magnetic field, this is the maximum magnetic field. Inside, MRI is active. Our code only works up to the bundle number of 1000. And this was for a quadrupolar symmetry. It's a linear theory, one can prescribe the parity. And this is for a dipolar parity. What we find is the lowest Reynolds number in this combination here, the lowest limit is for a quadrupolar. Okay, this is a good result. The lowest, the mode which can be excited by MRI with a given magnetic field. Yeah, the vertical magnetic field must be given. MRI does not work without any prescribed magnetic field. At the beginning, it's not a dynamo in the classical sense that you can start from infinitely small magnetic fields. You must start with a finite magnetic field. So, and for dipole, this is a higher one. This is okay. And now we look here. We are carefully observing the lower limit and the upper limit. And the result is the following. This is global quadrupole. Okay. Then the minimum field has a very simple, for all bundle numbers, a very simple result. The Lundquist number is of course 1. That means we can now compute the minimum magnetic field in galaxies for which the MRI starts. This is 10 to minus 25,000. It has to do with the small eta, of course. But must be careful. We cannot, our code does not work for bundle numbers of 10 to 12. We use the result for calculations up to bundle numbers 1000 in order to find here the numbers. This is a little bit inconsistent, but it's the only one. So a very small magnetic field is enough to start magnetorotational instability in galaxies. There are of course, no supernova explosion, not yet. This is a seed field. This is calculations for the seed field problem. The maximum field. This was this line here. This line. It's a linear, in this plot it's a linear line. The magnetic Reynolds number is proportional to the given Lundquist number. Order of 2 is the ratio is 2, so that the maximum field is 6 micropaths. More than, if the magnetic field, the prescribed magnetic field is stronger than 6, then the magnetorotational instability does not work. The magnetic field is too strong. It's a weak field, but there's a minimum. It's a weak field. Now to the pitch angles. The pitch angles on the left arm, the minimum branch of the curve, is this way, 0. On the right one, for the maximum, that's for the lower limit of the magnetic field, is 0. For the upper limit, it's 90. This is very strange, as, of course, differential rotation is working in the system. It's not excluded. The magnetorotational instability has interesting properties. In the middle between the minimum and the maximum we have. It's not problematic to produce pitch angles of 45 degrees. It's no problem. It depends on the Lundquist number and the magnetic Reynolds. Where are you in the bifurcation diagram? The next, this is the growth rate in units of the rotation rate, and what we find, it is completely different in the area of our parameters up to bundle number 1000. But this is very, very seldom that somebody produces solutions with bundle number 1000. We have one and the same growth rate, of course. In the marginal instability on the lower bound of the plot, it is 0. On the upper bound of the plot, it's also 0. But in the middle, it is the rotation rate. Always the rotation time. Always in this linear theory. So, summary: the galactic rotation law is always MHD unstable. For all the Prandtl numbers we computed, 1 to 1000. The seed field can be very small. We found 10 to minus 25 Always quadrupole symmetry is preferred. Rapid growth rate in rotation times. That means one rotation is enough or two rotations are enough. The pitch angles are no problem. Despite of the existence of differential rotation. The shearing, the system between the system and the MRI system can produce all pitch angles. Okay, now, Mark spoke about the problems of the MRI if the material is too cold. And this is one of the problems also in the theory of the star formation of the protoplanetary disks. Thus the question is, does for 10 Kelvin or 100 Kelvin the MRI work? You know, then the magnetic or the conductivity is so low that also the Reynolds number, the magnetic Reynolds number is very low. But the Hall effect is strong in such a situation. If the gas is cold, I do not claim here that the Hall effect is important in galaxies. I switch now to protoplanetary disks in order to present some new results, also linear and simple new results about such a system. We have now here, the Hall effect is clear, this is electromotive force perpendicular to the, if there is a current and if there is a perpendicular magnetic field, and we have in this direction a Hall electromotive force and proportional to the Lorentz force, and the new with the Hall effect, the induction equation becomes highly nonlinear or becomes nonlinear. Here we have curl B cross B. This is the new, including the Hall effect, the new induction equation. Of course, it can have dramatic consequences. We have a new dimensionless parameter, number 5. This is this delta, the beta here, the Hall term divided by the Lundquist number. What we know for protoplanetary disks is it should have an order of unity. This is without magnetic field, only material parameters are here. So what we see is this term runs with linear to the magnetic field and inverse to the square root of the temperature. That means Hall effect is important in two cases. Of course, if the magnetic field is very high, in the case of it is for neutron stars, 10 to 12 Gauss, or if it's very cold, if the temperature is very small, then this term is very large, and also the delta comes in the order of unity. The point that the Hall effect is so interesting is plotted here. You see, this is the Hall effect, this is the normal components of the induction equation split for poloidal fields and toroidal fields. Here we have interaction between toroidal and poloidal, poloidal and poloidal. It looks very like to a dynamo. From the poloidal field, if we have a poloidal field, then we get here a toroidal field. If we have a toroidal field now, together with the original poloidal field, we get a poloidal field. That means it's like an Albert square dynamo or something. It's interesting. And so far, the question, is it possible to construct with the Hall effect a new dynamo? Is instability possible? Answer, yes, I shall show it. Yes, it is possible, but only if some shear is existing. That means Kepler flow, or in galaxies, this 1/r rotation. Without shear, we do not find a dynamo. This is very clear. We had, in this case, we had no energy for us. The Hall effect do not produce energy. We need shear, the same as in the MRI. The energy in the MRI comes from the shear, not from something else. Okay, let's do some computation. What happens? This is the same computation with as before. The delta equals 0 is the old MRI computation, and now we produce for a negative field. imagine, we have in the induction equation a term B cos B. That means the sign of the magnetic field comes into the game. For a negative field, anti-parallel to the rotation axis, we find indeed, here's the minimum, we find indeed for Hall effect the critical Rm, that means the conductivity which is necessary for instability is decreased, is reduced. So Hall effect will help to solve the problem of the protoplanetary disks and maybe also for galaxies. Lower conductivity, that means cold, in cold air and in cold domains, lower conductivity is thus possible. We found only a small effect. And the referee of this paper formulated the question, is it not too small for a result? But the tendency is correct, and our code is unfortunately not in the moment not able to proceed to higher values of the Hall effect. It's non-linear, it's very complicated. But the tendency is correct, and here is also something interesting, but I have no time to discuss it. What happens for positive fields if the magnetic field is parallel to the rotation axis? We have quite another situation. In this case, this is for weak Hall effect, this is for strong Hall effect. In this case, the magnetic Reynolds number is increased. It becomes more complicated. No help for our problem. So it is, if we imagine that maybe for the star formation, protoplanetary disk, if we imagine that we have a disk and some external field, then the angular momentum transport outwards can only happen if the magnetic field is negative, not for positive fields. I mean the external field. The external field. Only in one case we can transport the angular momentum outwards. Not in this case. The Rm grows from say 8 to 10. This is the opposite what we expected and what we hoped. There is also another interesting effect, but I have no time. And the question is, how can it be? Is there some own instability? This was too fast. Here, this for strong Hall effect. One sees there's practically no influence of the MRI. There's practically no influence of the MRI. Question is this effect, does it mean own instability? Here we solved, after some papers by Water, by Stacken and so on, Urpin and myself, we solved the dispersion relation including the Hall effect. And what we found is indeed instability is possible, but only in one case. If there is a shear, if there is Hall effect, and if there is a magnetic field. But the sign of the magnetic field must be correct. The sign of the magnetic field must be correct. If this is negative, and this is the normal case, it is negative only whether it's positive by definition, then it is only possible to fulfill this condition if also the magnetic field is positive. Only in this case we have our own new instability, the shear Hall, we call it the shear Hall instability. It is not completely new. If you read the paper by Water, Balbus and Telkem, it is also discussed in the paper, but now we find it again with our global model. A new instability, and this is the shear Hall. This is a very characteristic plot here. Look here, the lowest, this is the necessary magnetic Reynolds number, this is the Hall effect here. If the Hall effect is too small, then nothing happens. You need a very high magnetic Reynolds number in order to produce the instability. If the Hall effect is very strong, then you need more shear in order to fulfill the condition that the shear brings the energy. So that we have also this, we can explain also this branch. What we see here is, again, the quadrupolar symmetry is preferred, the dipolar symmetry is not preferred. And here, this is one of our computations for m equal 1. We find that for large Hall effect, the non-axisymmetric modes can also be excited. This is an important finding in relation to the possibility of a dynamo. The dynamo only can work for non-axisymmetric modes. if we could not find here such a branch with non-axisymmetric modes, then it makes no sense, and we shall do it in the end of the year with an above to ask, is it possible to produce in a sphere with a completely correct model to produce a dynamo only with shear and Rolle effect? Nothing else, no turbulence, no supernova explosions, nothing. This is a very characteristic result that have also made already nonlinear simulations. A quadrupolar disturbance is embedded in a disk with a rigidly rotating core. Only the induction equation is solved, and we see that indeed Rolle effect and shear cannot be quiet. There's an instability. In this case, this instability has here some oscillations. This is I believe this is a rather new effect. We can also find the same. We can also deal or solve the same problem for Taylor-Coyette flow. We did it in the last years with the Mashalevka. That means if the magnetic field is positive, then you have a special, or is negative, then you have a very new instability also in Taylor-Coyette flow. If the outer cylinder is rotating faster than the inner cylinder, you can find a new instability. Before the Taylor-Coyette flow was only unstable in the opposite case, if the inner cylinder was rotating faster than the outer cylinder. Now we have a possibility, but this is the question, why do we not have experiments of MRI in the laboratory? It has to do with the simple fact that we have no materials and the fluid metals with a magnetic quantum number of 1. This would be good. But we have only 10 to minus 5, and for 10 to minus 5 you need a very complicated laboratory system. But I hope that in the next year we can indeed design some such experiments. Thank you.
Questions? Yeah, just two comments, really. Without getting into the fact of whether MRI works on the circumstances you're talking about, I think it's a red herring to say that there's no way you can use the C field, which uses quite a fault field by dimensional dynamics. It's completely wrong. Second comment is about pitch angles. You go back to the paper that was written by Anbar Superoff, Microsoft, and myself a few years ago with a dynamo which essentially was pointed to the dynamo. Again, we got pitch angles. We could get pitch angles around 45 degrees. It's not a problem if you think you need. So I mean, it's not. You don't have to go away to a more conventional dynamo.
And you need you made the alpha so big that it is possible. Of course, if the alpha is very big, then alpha is so big.
It's not orbital. With this crowdless form, those great orbital age, yes, you get that right sort of pitch angles. No problem.
Yeah.
You can make an experiment right now on the breakpoint if you wish. Right now.
I mean, a lot of pitch angles are 45 degrees anyway. Pitch angles are more like 20 degrees.
The alpha will be quenched at the end, and then it is small again.
No,
It depends only on the ether and
we're talking about rotational models.
what finally comes out.
Take the quench one. Corresponds to
about your model.
No, it doesn't have models.
I'm saying you get these results, no, you could, that's good.
No problem.
Okay, this is not the main point. What I demonstrated is that the pitch angles in the MRI, such floating models can be very large, despite of the existence of a strong shear. The shear is the shear of a galaxy.
Yeah, that's what we have.
And for the kinematic dynamo is a big problem.
Yeah. It's interesting, this dominance of the quadrupolar mode.
Yeah.
Is it doesn't depend on geometry? Is it the same in the sphere? If you try to the sphere,
yes,
that will be dominant in the sphere, right?
In the sphere we already found the dynamo with MRI, with Traeger 5 years ago. Yeah, but we didn't repeat the calculations. That's a good question. At the moment I believe it wasn't valuable, but we can see it here. Here we have wild explanation. We can read this there.
Any further questions?
respect the speaker, all of these speakers.
No, das macht das können wir doch noch eine Weile sogar.
Sorry? No, that's good to know. So the only is one of the Good, yeah.
Okay,
Yeah,
I've asked me if I mentioned to moderate this discussion here, and he also told me I should be very unprepared, which I am actually indeed. I think we had a lot of discussion here, which I personally found very interesting, and still there were questions open when we had to carry on with the talks, and so my first suggestion would be, should we pick up some of the questions that were actually quenched for time reasons, and so these things maybe we could discuss. In order to set the thing going, I just write a few keywords on the board which basically reflect what we were doing today, and so maybe while I write down, you recall all these questions that you had earlier and you didn't dare to ask, or you were just forced by the chairman to stop. So the first, we started with ISM structure, and there was indeed a lot of controversy, especially I think turbulence now is an issue we were discussing a lot. The second thing was particle acceleration. We heard at least 2 talks today, one yesterday, so there were different models. There was second order Fermi, there was first order Fermi also in the galactic halo, and there was this suggestion of the collisionless shock, where you had the vital instability and you actually induce magnetic fields that could accelerate particles. So that was yesterday, but it still fits into the topic. So if there are some questions, I would suggest we also can discuss it now. Collisionless shocks. So there was a lot of discussion, certainly about the dynamo, and I'm sure there will be more questions on that. And of course, related to that, the magnetic field. So you already see that the things somehow are coupled, because magnetic field, of course, was important for this one, it's important for the dynamo, it's important for the particle acceleration. So, and one other thing I would actually like to add, which was touched but not really discussed in detail, is MHD turbulence in the galaxy. Do we really understand it? Do we need it? Do we want it? Okay, so I just suggest you ask the questions and I try to soften down the emotions if necessary, or add some comments. So does anybody want to just jump on one of these, or should I add something? If you have some more.
Question 4. How long it feels important to all this business with ISM?
That's a very good.
Is it worth introducing this complication to the model? How very important to me?
Is there anybody who would like to defend that they are not important? Are you going to?
Well,
suggest that they are not important?
90% of people outside this room honestly believe that they're not very important.
Well, most people ignore it because they complicate things in many ways.
No, they genuinely believe that they're important. So, and very often it's difficult to prove yourself why exactly when you feel this essential.
Should I write down the energy equipartition?
No, the losses are slightly different, 10%, 30% different, okay, well, What is that? What are the crucial effects of magnetic field in the ISM?
Well, observations, for a start.
Most
You don't
don't care what they do.
No, but they are there, okay? I mean,
Would stars form without them?
Can
The night momentum form, you've got to
what?
remember
No,
momentum. So, I mean, the reason we're here according to the magnetic fields.
Well, it stops stars forming.
No, well, they can do it, but once the stars start to form, you've got to get rid of angular momentum. Yeah, the canonical way of doing it, and I don't know a better one, is by angular momentum transfer by magnetic fields.
Now, from recent more or less recent simulation of star formation, the fashion has changed. Now, people in star formation community, they do believe that the importance of magnetic fields was strongly exaggerated.
Why?
They have turbulence, they have supersonic turbulence, it's more or less easy to get high densities. That's from supersonic.
But you look at the magnetic fields there, they're not going to be doing nothing.
They said, well, it helps, but it's opposite.
I mean, they don't have a lot, we take holiday now to do something else to do the job.
I can tell you where from. I picked this up. Quite recently, I have discussions with Rheinbeck, where this SKA, new square kilometer array, those plans were discussed. And they were defining the key scientific problems which can be solved with this new radio telescope.
They need new problems.
And proving that magnetic observation of magnetic field science was fantastically different. Most of the even radio astronomers believe that they are not important.
Yeah,
well, certainly not right. I mean, he stresses the point that magnetic fields are fairly high in galaxies.
Yeah.
He gives numbers like 11 microgauss or so that frightens people.
Or the energy, the magnetic energy. According to Rheinbeck, it has the same value as the turbulent energy and the thermal energy. I have the numbers here. This is a good book. Find some connections. Numbers.
Well, I think magnetic fields are there by observation. I should not really be too ignorant of observations.
You have runs with and without magnetic fields.
Right.
Is there any qualitative difference between the two runs? And if yes, what is the difference?
Yeah.
What magnetic fields do with the multi-phase turbulent ISM?
Right, okay.
What's important? What's important is what important things they've done, if any?
Okay. I mean, what we were discussing mainly today, because I think it's important that it makes a difference to the classical models, was the volume filling factors. Here, they don't play actually a big role, because what is important for the volume filling factors is the outer flow. And that seems not to be possible to confine just by magnetic fields. This was my remark earlier. I think it's very difficult in ISM or in diffuse gas to confine anything with a magnetic field. I mean, we had this problem with terrestrial fusion reactors where, it's certainly impossible to confine anything. So why should it actually work on a much more dirty configuration in the ISM? So I would be very skeptical. But of course, something which you don't have without magnetic fields would be MHD turbulence for a start. That can actually, or that is very important for particle acceleration. Just to mention that, I'm not deviating from your question. So yeah, we see that, for example, the structures on certain scales with magnetic fields, they change. Because you tend to have, as you expect, flow more parallel to the field, because that's easier. If you have pressure gradients in your medium, it would preferentially stream along the field. So if you remember these movies, you had really structures now in C direction that were sort of largely hanging loose and the flow was going something round like this. That's definitely not the case without magnetic field.
No, but definitely, a nearby supernova will destroy all this stuff. Nothing can.
A nearby supernova, yeah, but you don't have any supernova at Z equals 5 kiloparsec or so. So that should make a difference. Of course, I'm still surprised that the dynamo people don't yell and say what do we need magnetic fields.
I'm just trying to be devil's advocate.
Yeah.
We do need a separate discussion.
That's fair enough.
The presence of magnetic field is observationally definitely is there everywhere. And I don't see a way you say that it is not important to you.
Yes, but there are many observation things you should observe, and still don't care to explain.
One is that the value which you get back to users is comfortable there, and that's why you give back a feel for it. And that's very comfortable. And I hope you said it is not good.
No, I will repeat an argument similar to Andrew's argument. That energy density of the starlight is similar to the same one electron volt.
No, but that's obvious. There's no
this is completely intimately related to the particle acceleration, all these kind of things. But you cannot just say magnetic density, we just ignore magnetic density completely. How can you do that?
That's because somehow the problem is that unless we learn how to answer such questions clearly and convincingly, we shall very soon stop getting grants.
No, but as I say, there are many processes that actually need magnetic fields. I mean, for example, if we talk about the viscosity, then the magnetic rotation instability seems to be a really good candidate that actually can produce viscosity orders of magnitudes larger than the molecular viscosity. That was, as I remember, always a problem for accretion disk flows or things like that. And people were really, having Sakura-Zhemyaev, ad hoc quantities putting into their models. Now we have actually a physical understanding of a plausible model, so that's something. And particle acceleration, as I mentioned, is very hard to imagine without magnetic fields. I mean, you would need electric fields, of course, but you don't have it in the ISM anywhere, because the Reynolds numbers, I mean, the conductivity is so high in the ISM that it's practically impossible to have large-scale electric fields. So all you're left is processes where you have magnetic fields that can somehow couple particles. So I think there are many situations that should at least, let us a little bit be more humble about magnetic fields. We observe them and we also need them in theory for some processes. They may not play such a big role, I agree with you, in some
But
cases.
it's so obvious that you don't let electric fields play any role in it. So if you have these models by Colgate, for instance, with a magnetic reconnection.
Magnetic reconnection is something I had here also, which I actually forgot to put down here, because I think it must operate, but I'm very insecure about what are the reconnection rates in a galactic context. I'm prepared to believe that we understand it, say, in the summer, so when we have strong magnetic fields, where we have standing shock waves, and we can have this sort of head-shake mechanism, which is fast reconnection, but the rate is at some 10% of the alpha in speed. But normally, we are left with something like the Sweet-Parker mechanism, which is, goes like with the logarithm of the Reynolds number. And that's much, much lower. It's maybe 1% of the alpha in speed or even less. And that really poses problem for reconnections of Parker loops, I think, in the halo. I mean, these halo loops, as you see, they are not always so densely packed. So you have to get them together and then start your reconnection process. And I'm not sure how fast this actually goes. Maybe you have an answer to that.
There is quite a recent paper a couple of papers by Drake and some other authors, some German authors, about the conditions for the fast magnetic reconnection. And the result is that, first of all, the pure MHD description is not sufficient to model correctly the magnetic reconnection. And second, if you apply the more general plasma approach, then the condition for magnetic reconnection is that plasma beta cannot be too high. I mean, something like plasma beta should be smaller than the ratio of the proton mass to electron mass. And under these conditions, fast reconnection operates always.
But in the galactic halo, the plasma beta should be fairly high, right? Because the magnetic field is very low.
Okay, galactic halo.
Why do you think it should be a little bit halo?
Basically, even conditions in the solar corona are very satisfactory for the fast magnetic reconnection.
Well, I remember a different model by Alex Vazarian, who sort of tried to
Yeah.
streamline the speed parking mechanism a little bit in the sense that he was trying to have more sort of reconnection points along feed lines and thereby increase the reconnection rate and not just the sort of this,
but this is
model
still described by the MHD model, which is not sufficient. I mean, the there is in the series of papers, there is a comparison on different plasma approaches and MHD, and the MHD provides provides always the Parker speed mode, because even if someone wants to trigger the Petrak's mode, it collapses and forms a very wide current sheet, which slows down the reconnection rate to the logarithm, to the Reynolds, to the alternate speed divided by the square root of the magnetic Reynolds line. But this is not the case of the for example, two-fluid description of plasma.
Physically, what is the difference?
What is the difference? That the criterion for the fast magnetic connection is the existence of dispersive waves, like, for example, the Whistler waves or kinetic alpha waves.
If you have a two-fluid theory, you're freezing your magnetic field in the electrons, the ions are not frozen in the
And what does this mechanism work fast enough, say under conditions of the galactic halo, where we have low magnetic fields and very low densities and hot gas? Is this an environment you would think that is really
I think that only magnetospheres of neutron stars are in charge.
What do you mean? It works anywhere except there?
Yes.
I haven't heard such a strong claim. Anybody who is...
I try to compare this Drake's criterion to the real astrophysical conditions, and this is published in a paper of 93 in Astrophysical Media Character.
But there is still the problem, if the field lines have large separation,
why separation?
Well, because if the field strength is lower in the halo, they can fill a larger volume. You would have an average, but just if you
current transforms spontaneously.
Yeah, but at least in the reconnection process, you get to have antiparallel field lines somehow together. Also, this mechanism, I suppose.
It's not exactly antiparallel. It's enough to have some more finite information.
Yes. But even that, suppose they have distances of kiloparsecs or
this is not a current sheet, it is a distance.
Yeah, but that's exactly my question. You have to compress the field in order to really make this mechanism work.
I think that the disturbances provided by any kind of explosions in the disk are sufficient to form two independent loops will meet the sun.
How ambipolar diffusion would have to get these sharp gradients?
At least in the context that we have talked here so far, we are talking about a situation where the fields and the flows are turbulent. So we always have the possibility of generating smaller and smaller scales. And the smaller the scales become, the smaller does the velocity and the magnetic field difference becomes. And so at small enough scales, the magnetic resonance eventually will become unity, and you will of course have just ordinary diffusion. So that's how we should at least be able to get rid of the energy, by ordinary dissipation, dual dissipation.
Yeah, but the problem is, I understand, in the halo dynamo is that of course you must have some dissipation mechanism out there where the field lines are maybe more regular, I don't know, but or they are not so much tangled as they would be in the disk in the vicinity of explosions.
But is that's based on analogy with the solar corona picture, or what?
No, that's what I see from the simulations we made. We produce rather large scale field loops or whatever. But okay, I'm not insisting on that.
Once they are in the corona, those loops, I believe, will really eventually eject into the wind. That's also what we see in the sun.
Maybe.
Parker spiral, for example, right? That is part of that.
You want to show some movies?
No, just 2 pictures. Because we've been talking about this relation several times, so I just wanted to show it. This is the empirical BN relation. And it shows that it's pretty close to a 1/2 slope, and it spans over at least 6 orders of magnitude in density and 3 in magnetic field. And it's an upper envelope. You can find lots and lots of observations, especially if you ask observers off the record, much below at certain densities. But the upper envelope is a pretty nice correlation.
If you would take the upper limit there, what sort of element speed would you?
Yes. Density 1, few microgauss. You can figure that out.
Well, it will be 30, right? If B scales like rho 1/2,
Yes,
then how the speed will be independent.
Oh, yes, but
30
what is it?
30 kilometers per second.
Okay.
Between that.
The other one I wanted to show is this one. This shows what you actually would observe if you had turbulence in a molecular cloud. And you know, these are some detections in red, and the blue are from a model, and they both agree. And the amazing thing is that the average field here in the model is 5 microgauss. And nevertheless, you observe some spots with more than 100 microgauss. So it shows that it's terribly difficult to go from observations and back to some kind of mean magnetic field. It's so intermittent that you can measure anything, and it's impossible to derive the mean field from the observations. I just wanted to show those two.
Yeah, but I think it agrees with what we actually showed in the calculations.
Yes.
We get a very large trend. And I would also say that if you go down to higher densities, then of course the relationship becomes more valid, probably than these cases brought in the one case.
What about the issue of the importance of magnetic field for star formation, which was also mentioned?
The issue
of the importance of magnetic field for star formation. Can you say a few words? What would happen if you didn't have magnetic fields and you were forced to make stars?
Yes and no. I can't really say what would happen because we haven't really figured it out yet. Naively, from the way we derive the IMF for an MHD case, you would expect the slope to change. You would have a steeper slope if there wasn't any B field, because you would have a different. You'd have a higher compression in the shocks.
Yes.
But we have a suspicion that things may conspire to get back to the same slope if you include rotation. Vorticity could play the role of magnetic field. But the main problem is that if you don't include a magnetic field, you must have a much higher resolution. Magnetic field really helps when you do turbulences because it increases gamma. So instead of having isothermal conditions, you have a gamma of 2, which is much more easy to handle. And there was one thing I wanted to ask Miguel, but he may have left. But as a general observation, when one does AMR is not just AMR. It's a question of what you refine on. And people at San Diego have discovered that it really makes a difference. There you are. I wanted to ask you about refining. What criterion one should use for AMR is important. It turns out that you need to not just refine on, say, pressure contrast, but also on shear. You can try, for example, to compute a Kolmogorov spectrum or a turbulence spectrum, a power law, with adaptive mesh refinement. If you refine only on pressure, you lose the power spectrum, unless you refine so little that you cover 70% of the volume and AMR is no big deal. But if you refine on both pressure and shear, you can do with much fewer meshes. So it shows that there are more than, of course, just shocks to catch in turbulence. There are also shear discontinuities. And if you resolve several of these criteria, then AMR can be a really great gain, even in just isotropic turbulence. But only then. Otherwise, you run the risk of really losing correct results. So I just want to ask what kind of refinement do you use? What criteria?
We refine on pressure gradients and when you have steep gradients on nested valves and then pressure will be different.
But not on shear. I think you should try. It might even buy you something. It's not that you're going to have more zones. You're actually going to have fewer zones for the same quality result.
Okay, there was some more people who wanted to.
Showing this relation between density and vegetation. If you have a collapse situation or a condensation, then of course this depends on the geometry of the magnetic field, how the density increases. Therefore, it's nothing surprising in that get much lower densities or much higher densities for some magnetic field, because if the matter slips along the field lines, you increase the density without increasing the
Yeah, I mean that's clear. But here we have situations where you have lots of field tangling. You don't have really large-scale fields where you can just throw them along. And so if you have a high turbulence.
Yes, but if you go to really high densities in molecular flow.
Oh yes, there, as we say, the Chandrasekhar turbine holds pretty well. But as you go away from that, it becomes pretty bad. Right, was there something?
Yes, it's nothing I'm working on, but it's just a general question. So, concerning the turbulence in the outer parts of the galaxy.
Can you speak up a little bit?
Concerning the turbulence in the outer parts of galaxies, for example, simulations show that you can produce turbulence distortion, you can have MRI. But also maybe there is something else, which is that those outer parts of galaxies are not dominated, are not self-gravitating, they are dominated by dark matter. And I mean, there is models of halos now, of dark matter halos, are light halos, and they have irregularities, and so they interact with the ionic matter. So I don't know if I'm not particularly working on that. It's something just that I know from people in my institute. For example, Hans-Walter Riggs was trying to explain the wiggles in some philosophy terms with dark matter. I mean, maybe in the inner parts this has no effect, but in the outer parts, those parts are definitely not self-gravitating. They are influenced by the gravity of the halo of the dark matter.
Well, we think that there is one because you need a flat rotation curve.
Yeah, but the rotation curve is exactly not flat. In many galaxies, it has a lot of.
Or it wiggles,
It has a lot of wiggles.
Even if it were flat, you would need a sort of dark matter halo, otherwise you couldn't. Otherwise it would vary.
No, sure, but the idea is that this dark matter halo is not static anymore, like in standard models. But I think
at least for anything that like if somebody is interested in that part. Yes.
Good morning. Anonymous cosmic rays was mentioned, acceleration like solar wind boundary, if anonymous cosmic ray was mentioned, and then people were asking about the diffusion inward of the galactic this one. So I just wanted to know what exactly is the thing which is being. So I didn't get the point why the anomalous cosmic rays was brought in for the comparison of the halo acceleration.
The anomalous cosmic rays are produced from the ionized pickup, from the pickup lines in the solar wind. So basically they are accelerated at termination shock, and they there have a powerful spectrum. When you look at the spectrum at one NU, this powerful spectrum gets overall. They are modulated like the rest of the cosmic rays. And actually what you get is a bump near the maximum energy that you can actually accelerate. So anomalous cosmic rays are basically just bumps for example, in those elements that may have a neutral component in the solar. So my idea was that actually it's if you are looking at something that gets reaccelerated somewhere, and then has to be coming in towards a flow, then you might actually see something according to which would resemble the area of the knee, so that you would have a little bump and then a cutoff. So this bump and cutoff would be, or steepening of the spectrum would be similar.
But it's so different from what you are having in the industrial conditions. How can you have the same kind of phenomena taking place there? Because the interplanetary conditions, you know, the things are very, very different from what we have.
But the basic thing about diffusive shock acceleration is simply that you have to have short enough mean free path so that the diffusion length of the particles is actually much, much less than the area in the upstream region they have available for the accelerator. So this means that there has to be modulation.
It's basically a modulation problem, yes. And I think it doesn't matter in this case here. But, of course, I mean, shouldn't it be somehow reminiscent to the modulation of the solar wind, where it affects actually the particles at the lower energies, but not the particles at the higher energies, because it depends obviously on the diffusion coefficient. So when you accelerate the particles up to higher energies in the halo, they might have a possibility to get back without being too much modulated by the outflow.
Yeah, exactly. But if you allow the high energy particles to have high mean free paths, you can reduce stress for the Fermi more to accelerate.
Oh, this is already after they have been accelerated.
No. You have to still, if you want to make the high energy particles out of something that the supernovae have accelerated.
Yes.
The supernova spectrum will have a cutoff maybe at 10 to 15.
Yes.
Now you want to explain the region between 10 to the 15 and then 10 to the 18. You still have to accelerate 3 orders of magnitude.
Yes,
With a power of spectrum of e to the minus 3.
Yeah, but this is a different kind of shock wave. That's the main idea here, because it's not a supernova random shock wave, it's a large scale and long-lived shock wave that can actually give you longer acceleration times. And then,
but even in steady state, if you think only about the steady state progress, then you could perhaps think about a shock wave that is standing right there. If you have a flow that is coming towards, that would be resembling your reversion, perhaps. And then this particle that is being accelerated in this long-lived shock, it would have this upstream, more or less upstream decay if it's being accelerated. So that when you move further and further to the upstream, you will have this exponential decrease of the intensity. And this is basically what you are seeing right here. If the acceleration is done.
but if the diffusion coefficient gets larger with energy, as you don't accelerate anything. No. But then you lose the cosmic ray particle from the shock, and then it has a possibility to diffuse inwards to the galaxy. This is where it can be observed.
Yeah, but now you want to accelerate particles with energies up to 10 to the 8 eV. That tells me that your mean free path has to be so small that particles of this energy can be accelerated. So there's a little chance of perhaps particles with energy of 10 to 14 or something like that to ever get back if you have a, let's say, normal type of mean free path that increases with energy. Of course, if you have flat energy independent diffusion coefficient, then you could perhaps play with parameters to get to something like that.
I don't see why, after you have accelerated your particles, why you shouldn't be able to get them back. I mean, the diffusion coefficient, as I say, increases with energy.
So that's the same diffusion coefficient you use to accelerate your particles. And there you need a shock, and then to get them back to the large diffusion. That's my point.
But they will have a large need to come up so they accelerate. That's my point.
Well, it's not a step function or anything like that.
Okay, maybe we should address other points if there are. We still have a couple of minutes left. Yes.
For me, always one of the key questions is the RMS velocity, is it increasing with z or decreasing with z? Yeah, there are some good reasons. We know this turbulent diamagnetism. That means the mean field is expelled from the regions of high turbulence intensity and transported, attracted to the regions of smaller turbulence intensity. And so far, this is very important for the dynamo. For example, this David, he works in this paper. He mentioned he works with a buoyancy. That means the magnetic field is driven upwards. But if the turbulence intensity is growing with that, then the opposite is true. Then it is there's affection. So far, I'm always interested to see what is the result of the simulations with respect to the turbulence, to the vertical profile of the Hall method.
Any comments or answers to this question?
We'll probably just make you. We can't become totally right.
I mean, trying to see turbulent effect though, that model, if I remember correctly, had a increased upwards, we increased the turbulent velocity, the driving unit velocity. But in some sense that effect was talking about was there, and it was not dominate what was going on. We included representation.
Yeah, but if it is true that there's a strong gradient in Z, then all the models should the mean magnetic field are produced in the equatorial plane, not in the halo.
In fact, all the models we make have a strong gradient in diffusivity upwards, and we include the appropriate predetermined driving units downwards. I mean, it's always included. So I mean, if the effect is there, at least on that mean field level of representation, we should be seeing it. It's an important effect.
The pumping is
downward.
The pumping is downward or not?
Sorry?
Is the pumping downward or upward? Downward.
Yeah, of course, yes. So I mean, it's included as a mean field.
Yeah, but then the magnetic field of the models cannot be at 500 kilometers.
But they are where they are.
Right, others?
One short question with this spark instability, which is obviously an important physical element. And I think we have already thought about this. Is there any observational observational evidence of spark instability as an item? Somehow the effect is strong, physically simple. It would be strange not to see any observational evidence.
Well, I remember that Marek Urbanek sometimes showed some plots where he claimed that these are actually Parker loops that you see. I am not enough of an observer to say if this is really compelling or not, but
It's difficult to distinguish Parker loops from the reading of bubbles.
But still, everybody said that they see bubbles. Well, nobody said that it can be Parker loops, right?
probably this is about
just because near every such bubble there is a center of conduction. Parker loops will differ from bubbles by the absence of or the associations or whatever can blow the bubble up.
Yeah, but then it may happen that you have an OB association somewhere which finds an easier way to blow out here, and then you have a loop here, and then you say, I don't see a star-forming region here.
That's fine. So everyone said that they see clear observational evidence of superbubbles, but nobody said there is observational evidence, even not clear, of Parker loops.
Yeah, I mean that's not surprising because if you have a superbubble, then you have of course the power machine here, and that's the easier thing to observe. Parker loops would be much more difficult to observe. That doesn't mean that they don't exist, so. Right. So we are actually coming to the limit, or is there some final remarks, some final comments, something somebody wants to say without or before leaving? If not, I thank you for your contributions, and I hand over to Axel Brilliant to say something.
No, I mean, I wish everybody a good walk to the restaurant. So make sure you have your map and just follow common sense, of course. It's a small street, beautiful small area, it's a program cinema, basically upstairs, so that's how it looks like, and then you go to the first floor. It's not on ground level, of course.
How far in the way? 10 minutes walk or 15 minutes walk from
It's more like
Winter, for example. So 15 minutes walk or
maybe 15, yeah.
Here? No,
from